So in this lesson, he talks about three kinds of neural networks: ResNets, UNets, GANs. Oh, it's four kinds of networks: ResNets, UNets, GANs, and RNNs. So he starts with a ResNet, and he builds. Let's see. Oh, he refers to the paper where the ResNet was first introduced, I guess. Deep residual learning for image recognition by Kai Ming He and three others. So the ResNet is an invention that allows you to use deeper layers, deeper networks, and they have much better learning ability. The deeper the network is, the more learning ability it has. The problem with deeper networks in the past had been that it quickly gets out of control, and it takes too long to train, and you I guess you lose ability to solve for the weights very well. So they invented this thing called the ResNet, which helps by what it does is it makes a skip connection between earlier layers and the layer that's a couple of levels down deeper. And what skip connection means is that it takes the input and supplies it to the adds it to the input of the layer downstream. Either adds it or concatenates it to the input of the layer downstream. And what that does is it allows the network to remember more of what went on earlier, because in other words, that data is available. It's folded into the. In other words, when you add the earlier inputs to the later downstream levels in the network, it makes that data somehow available or folds it into the memory of the network. So he builds, let's see, I'm trying to see what his first application was. Let's see. The first notebook that he uses is the I think he built something to solve the MNIST data set. And the MNIST is, it's a data set that has been beaten to death, and it's got, it gets really good results like 99.998 or something like that. But he just shows as an illustration of what this can do. He puts together the ResNet and turns it loose on this MNIST problem, and then right away it gets 96 without any tuning at all. And then after some tuning steps, he gets up to 99.4 or something like that. So that's the first notebook, the MNIST notebook. There's an interesting aside in this lesson. He says that what he's been doing is he takes, or one of the secrets to his success is that he takes old papers, he reads old papers, and then he looks at them and says, how can we rebuild this work using more modern stuff that we know now? Like, 5 years ago, they didn't have all the tools that we have now. So he takes old papers and tries to rebuild them, make them even better using more modern methods. And I think he's done that with some of the notebooks in this lesson, although it's not clear which ones. Let's see. So, okay, and he makes a distinction between ResNet and a dense net. A ResNet is when you have a skip connection and you add an input from an earlier layer to a layer that's downstream. And the difference between a ResNet and a dense net is that instead of adding the input from an earlier layer, you concatenate it. And so dense nets, the problem they have is that they keep dragging the data from earlier layers along, and they get bigger and bigger as you go downstream in the network. But then he shows that there are tricks to help to fix that. So you can imagine that if you concatenate the data from an earlier layer, now you have twice as much data, and then you concatenate that from later, and then you have more activations than you had before, because you keep concatenating the ones from the earlier layers. So he says the way around that is to do stride transformation, that convolution transformation where you skip pixels, so that you reduce, every time you have too many inputs, you just do a stride convolution, and that compresses it by a factor of 2. So that's how to keep that under control in a dense net. As far as practical applications of dense nets, he says that these are good for problems. They don't have a lot of parameters compared to other kinds of networks. So they're good for problems that have a small amount of data, because you don't have to solve too many parameters. All right, so that's the ResNet and the DenseNet. The next thing he talks about is this UNet, and he refers to a paper called Convolutional Networks for Biomedical Image Segmentation, because that's where this concept of the UNet came up. It came up in a sort of an isolated medical application that nobody ever heard of until years later, when people started realizing that these are good to use in segmentation problems in Kaggle. People started applying this UNet paper to Kaggle competitions, and they started winning them. Kaggle competitions that involve segmentation.
Apologies, I just joined late. I just forgot that there was a change in timing. I'm really sorry.
Okay, BJ, over to you. I'm going to stop share, and then you can take over.
Okay, I'm really sorry about this, guys.
And thanks for stepping in, Joseph. Appreciate it.
Okay, I hope you guys can see my screen.
Yes, we can see it.
No, I can't see it.
Should be coming up any minute now.
Okay. Yes.
I can see it.
Yep.
Okay, great. Fine. So again, let me start off with an apology. I just forgot the 1 hour time difference that, because of daylight saving time has got back now. So sorry about that. Okay, let me get started. Lesson 7, a pretty intense lesson of all the lessons that at least I have seen. A lot of concepts to be covered. And so let us get started without too much of delay on that. So this is what is there to be covered in this lesson, and let us see based on the timing how much we get to cover, right? So what all Jeremy covers is basically uses the MNIST data set, and he goes through one, which is a data block API as to what are the contents in the API.
Sorry, Vijay, it's Jonathan. What I suggest is, why don't we start from UNet? The only reason is Joseph has kind of covered the MNIST bit.
Okay.
I think there's value in us starting from UNet, because that's also a little bit more tricky than the MNIST.
Absolutely, no problem.
Great.
So let's get over there. Okay, I think so. This should be where I think should be a good introduction for UNet. So I hope that basically where UNet is involved is you're concatenating the sets, the identity connection instead of adding them, right? So that's where the units come into being. They're always also otherwise called as dense nets. This is completely memory intensive because you're concatenating the inputs to the outputs that is coming in from a particular activation, and thereby it makes it more heavy and therefore memory intensive, and thereby it is suitable for small data sets. It works very well for segmentation because you're basically trying to get the fine-grained details of the output that you want to get generated. Therefore, when you concatenate, it makes it much more easier for that model to perform, right? But then this particular model doesn't work always that way. From time to time, what we do is we squish the outputs via a regular convolution layer, and then we start again to concatenate and go along, and then we introduce something to squish it, right? So that's how it works. So if you see what is the network architecture of a unit, it is this, right? So basically what it means is you have a contracting part, basically a downsampling part, and then what you have is an upsampling part, right? So the original paper of UNet that was there, this is how it had defined the upsampling, the downsampling and the upsampling part. So you had 4 blocks in the downsampling part, and each block had the following. You had a 3x3 convolution layer with an activation function and batch norm, followed by again a 3x3 convolution layer with the activation function and batch norm, and then a 2x2 max pooling layer, right? So that's how each block was there, and you had 4 blocks like that. So that should explain 1, 2, 3, and 4. Then you have a bottleneck layer over here, right? The one at the very bottom. That is again 3x3 convolution layers with a batch norm, and they have introduced a dropout, right? So if you go and check the implementation of this paper, somehow the dropout doesn't seem to be there. That's what I read in the paper. But in the mention, they have mentioned that there is a dropout included. And then we come to the upsampling path here, right? And this is again the same 4 blocks, but then what we are doing here is deconvolution, right? Basically, we need to increase the feature map size, right? So when we do the downsampling, we do the stride 2 convolution, and therefore there is a feature map reduction, and that's why we call it the downsampling. Whereas when you come to the upsampling path, we need to increase the feature map size. So for example, from a 28 feature map size, we need to go to a 56 feature map size, and so forth. So how do we do that, right? So basically, we need to do that with the deconvolution of stride 2, and then we concatenate with the corresponding layer that is there in the downsampling path. And then we have the 3x3 convolution layer, and again followed with the 3x3 convolution layer, right? So that's how the unit architecture is that is there, right? I hope this is clear to all of you,
Yes, it is. Thank you.
Okay, great. So fine. So before units were involved, the traditional way, how did we involve to increase the grid size or the feature map size was the following. We could do a stride half convolution, also called as a deconvolution or as a transpose convolution. So what did we do there is basically we took the pixels and then we added 2 pixels of padding in between and around them, right? So that's what we did. And it is very well explained in this paper called A Guide to Convolutional Arithmetic for Deep Learning. The link is there. It was explained by Jeremy also in the lesson, as well as you can find it in this particular presentation when I upload this into the Slack group after we are done with it. So basically what it happens is you take a 2x2 input, which is a kind of a grid size that you have. You run a 3x3 kernel on top of it. And because you pad it with these 2 pixels in between and around, what I get is a find-to-find output. And let us see how that happens, right? So basically this is it. So you have a 2x2 pixel, which is A, B, C, D. And what you do is you put 2 pixels of padding in and around it. So say this is A, this blue one here. You put 2 pixels of padding, and that includes the existing B as a pixel. And then you have 2 pixels this side, 2 pixels up, and 2 pixels down, right? So that ways it becomes now a bigger size. And then when you run a 3x3 kernel on top of it, so this is the 3x3 kernel, the gray one, what you get is a find-to-find output. So that is what is represented in this dark green version here, right? So that's the way before unit people used to do to double the grid size. But then,
so,
as you can see,
question for you, Vijay. Why I thought the objective was you got a 2x2, but you want your final output should be a 4x4, right? Because you're doubling, you want to double. So you've actually ended up with a 5x5. So how is that a good thing?
Okay, so I'm not saying this is exactly the way to get to a 4x4 size. What I'm saying is this is the way people used to do to get to this size. So if you want a 4x4 matrix on top of it, probably you will have to skip one kind of pixel in between, probably, right? Then you get to a 4x4 kind of a size. I'll probably, when you get to the next set of things here, you'll be able to understand it much more clearly.
Great, thank you.
And therefore, okay, so going forward, so basically this is not an efficient way because we are adding pixels and they're just white pixels on here. And then a lot of competition is involved because you have added 2 pixels and you have to run the kernel through them. And what was effectively a 2x2 pixel now becomes a find-to-find output that you need to kind of consider. So what is the other way of doing it? The other way of doing it is the interpolation method or the nearest neighbor method, right? So basically what we do is we take this and we replicate it like this way, right? And then if we do a stride 1 convolution, you will get a 4x4 output on top of it, right? So that's one of the ways to increase the grid size. So to answer your question, John, I hope now it's clear, right? So this is another way of doing it. So this way you'll get a 4x4 output, but with a stride convolution of 1. Hello?
Yeah, excellent. Thank you.
Yeah. Okay, so one more method to do it is not just do a stride 1 without any weights. The way here in bilinear method is to give an addition of weights to it. For example, you have this pixel A, and then you see what is around them. So you have 3 pixels of type A, 2 pixels of type D, type B, 2 pixels of type C, and 1 of type D, right? So you basically assign weights to them, and then you try to multiply them to get an output from that, right? So that is another way of getting the grid size from a small amount to a bigger amount. So basically try to do a deconvolution. So this is one other way that is there. And then Jerry goes on to mention that he will explain how in part 2, in the case of Fast.ai, they have come up with something called a pixel shuffle or a subpixel convolution. So this is one of the things that we are to wait for example, to understand how this kind of works. But so this is basically how it used to happen before unit, right? So this is the way they increase the feature map size. So let's see what happened in the case of unit. In the case of unit, they did a concatenation and they tried to increase the feature map size because they are concatenating it, right? So basically, if you look at the thing here, you have the 54 output and you're concatenating with an output from 6 to 6. So basically now you're able to get a bigger feature map size than what you started out with. Now you're not doing a stride half convolution. You're not doing an interpolation of nearest neighbor. You're not doing a bilinear interpolation. You're concatenating the output from the corresponding downsampling path. So by that way, you get all the features that are there because the downsampling path obviously has more feature maps in it. And when you concatenate it with this upsampling path, those details that are there in the downsampling path gets added to this upsampling path, and they become richer with those details. And thereby, when you run the convolution on top of them, you're able to then get the output that you so desire to be able to retain the original texture of the image, the finer details that you would want to see, right? So that's how, in the case of unit, they're able to come up with just a skip connection. So this skip connection is also what you saw in ResNet as well, right? The same skipnet connection, but just that in the case of unit, it is not just after every convolution, it is just in the corresponding downsampling with the corresponding upsampling path. So that's how it's been.
One question, please, Vijay. So you've on the left, for example, you've got something that's of size 136. On the right, you've got a size 104. How do you then ensure that they're the same size so that you can continue to work with the image when you do the concatenation on the right?
Okay, so the picture that we have here is based on the original paper, John, right? So they may not be the exact way of representing the particular thing, right? So in the case of unit that we have, your numbers will not be the same. It will be completely different and will be equivalent to the size that you want to obtain. So for example, if this needs to be, for example, here where my cursor is, it needs to be 56 and it needs to be 112. The corresponding downsampling path will also be 56, not 66, for example. Are you able to follow me?
I think I understand what you're saying, but in this example, right, the one that they've provided, how would, because it's clear that, when you do your convolution and so on, you're changing the size of the filter. So for example, now it might be, after you do a convolution, right, with the stride 2, it goes from 138 to 136. When you're concatenating that 136 to the 104, right, because you're probably going to end up with that sort of situation regardless of what.
Okay. So I think you should look at the numbers on top, which is 256, 120. That's the one that you need to look for in the case of feature maps, not the 284, 280 that I understand, right? Because when you do a stride of 2, you're increasing the feature map size from 64 channels to 128 channels.
Yeah.
Right. So that's what you get added again in the corresponding upsampling path. Are you following me?
So obviously I've got something wrong here. So what is that? So the 256 is corresponding to the size of the
image,
right? So 256 by 256.
So I think it is the size of the image, if I understand it right.
Yeah, okay. And then what's the 136 there then?
So 136 is the half of 280. It should be, should be 140. I don't know why it is 136, but basically it's the half of that.
No, because I think when you do a max pooling, you're going from 280 to 140. So that makes sense, right? And then when you do the convolution, you're going to 138, 136. That bit makes sense. But what I'm trying to understand is what is that number 136 and 256?
To be frank, I don't know how they got this in the original paper, but if you see the mathematics here, if I go to the blocks, so you have a 3 into 3 convolution layer, and then you're following with the max pooling, right? So there is something that is happening in these two layers, which is causing that particular number to change.
Sure.
You have to go into the mathematics to find out that.
No, that's the stuff that's actually happening in this layer, because when you do your 3 by 3, right, when you're doing your convolution, that's changing your number. So, when you're doing it with a stride 2 and so that makes perfectly good sense, because you're going from 140 to 138. When you go from a max pooling, right, you're going from 280 to 140. So that stuff makes sense. I think I'm just trying to figure out what those numbers mean, because I'm trying to understand how, when you're trying to reuse the data from the image, right? So you're across, you've got this arrow going across where you're trying to concatenate. Obviously, when you concatenate, they need to be the same image. And what I don't understand is, and what I want to confirm is, are they actually going to be the same size so that you can concatenate them?
So I think 256 is the number of kernels, the width, and the 136 is the image size.
Yeah, okay, then you got a problem there, right? Because you got a 136 image, and then going across, it's a 104 image. So how is
so that's the reason they are taking the center part, not full. So that's a dotted line is there. So they are not fully taking 136. They're just taking dotted part of that and concatenating with 104. So
right. Okay. Right. Okay. That might make sense. Okay. So he's so just for your Vijay, what he's referring to, that dotted part.
Understood.
Yeah. Okay.
Basically, this dotted part here is what they consider to be added as a concatenation layer here, right?
Yeah. Okay.
Yes.
Thank you for that. That helps. Thank you.
Great. That was a really good insight. Thanks. Okay, fine. So now we get on to the next step that we have, basically how to use them to get image restoration done, right? And there are a number of things that Jeremy mentions you can do here. Basically have a low-res image into high-res, convert a black and white image to color, take an image where something is not there and try to find what is that is missing and put it there. Take an image and kind of make it look like the painting of Monet or Leonardo da Vinci, and then do multiple stuff with it. So these are all things that you could do as a part of image restoration. And in the case of us, what we're going to do basically is to convert a low-res image into a high-res image. So that's the first thing that we do here in this particular tutorial. And what we use to do that is basically called as Generative Adversarial Network, or GANs, right? And this is how Jeremy explains the architecture of this particular network. So you have an image which is crappy. So in our case, this is something where you take an image and you make it a low-res image, and therefore you have that as your input. You pass it through something called a generator, right? And this generator is again nothing but a unit. It'll have ResNet34 as its backend, and it'll try to convert this particular image, which is of low-res, into a high-res image, right? So that is the prediction that you see here in this brown box here. What we will try to do is to get the mean squared loss of the pixels between this predicted image and the target image that we already have, right? And then what we do here is send both of this into another model called a discriminator or critic. And then the purpose of this is to say, is this discriminator able to differentiate which is a predicted high-res image versus which is an actual high-res image? So that's what is this particular network is all about. And the name of the game here is to do multiple iterations so that the generator gets better at producing an image that actually looks like a high-res image, and the discriminator gets better, or is not getting better, it's basically getting it tougher, finding it tougher to discriminate between this predicted high-res image and the original high-res image. So that's basically the network as we call it. Right. So this is what I explained as well. So you have a unit learner with ResNet34 backend. This will give us an output image. here we have 3 data classes. If you see, it says data.c is 3 in the code. I will show that as well. So basically, as per what I understood, it is because of 3 things. We have an input, we have a prediction, and we have a target. There is no explanation of this, but this is what my intuition tells me, unless somebody here is much more clear about it. And there are a number of things like wire range, blur is true, self-attention, etc., which we will understand in part 2. That's what Jeremy mentions in this particular class as well. Okay, moving forward. So in the case of a critic, what we have is it has a GAN critic learner already. We are not using this ResNet 34 here, because what Jeremy says is, in order to get this critic working, we need to do something called a spectral normalization. And that is probably not done using ResNet 34. So that's why he has already something called a GAN critic learner done in Fast.ai. So interestingly now, this is where I think the crux of the matter is. The loss that is there in the critic is adaptive loss of a binary cross entropy loss. So this is what we will use in the generator ultimately to find out, can I get this loss function to be minimal so that the critic finds it very difficult to differentiate between a high-res image and a low-res image. So that's basically the part of it. So let us get into the okay, the workings of it. So what we're going to use here is the Oxford Pets image. What we will do is to take this image, and on that image write an integer, any integer between 10 and 70, and then we will save that particular image, making this particular number as the quality of the image, right? So that's basically the crapify part of the database, or so not database, of the low-res image that we're going to generate. So that's basically what is here. So we will import the modules as we see it with the Fast.ai, Vision, callbacks, vision.con, whatever. And we're using the Python image library. And using this Python image library is what we will draw that particular integer and then save this corresponding image that we get after having written that integer anywhere in the picture, and save it, the quality of that picture, to be equivalent to the number that we've written there. So basically anything between 10 and 70 is considered to be low quality image, right? So that's what this crapify function basically does. So you can see here that it says image.draw.text anywhere between 0 and width by 2 of the image and 0 and height by 2. This is basically the XY coordinates. The string is basically the number between 10 and 70. And then we fill it with a color, which is equivalent to this number 255, 255, 255. And then we basically save it at the destination, which is the crappy image folder with that particular quality. Right. And then we go on to do the next part of it. We do the image list creation, and parallelly we do the crapification process of that particular image list that we generate. I don't know if you guys saw this image item list. Probably now seems to have changed to an image list or item list in the new library. I was trying to run this particular thing and I was having a problem running it. So it has kind of changed, I believe. So then you do the parallel function to be able to take all of this, images which are high-res, which is basically the path.hr is the high-res image. And then you write this function to change all of it into the low-res image. And then, of course, we get to the next part of it. We find the labels. We do the transformations. The transformations here is we're only doing the zoom. And then we convert into the data bunch. We normalize using the ImageNet stats because we're going to use ResNet.34 as the backend. So that's what we do. And this is what, as I told you, my intuition is data.c is 3, basically because there are 3 types of things that we have: input, prediction, and target. Right. So basically, when you see the output of a trained data set, this is what it has. You have an image list, which is X, and an image list, which is Y. So basically, the low-res image versus the high-res image. Then we mention these things. So some of these things, as I said, is what we will learn in part 2. Why there is a Y range. Why do we say blur is true? Why do we say norm-type.weight, self-attention, etc. These are things that we will learn in part 2. So now that we have this learner, we create this learner, which will now do the generation part of it, right? So that's what it says, create GAN learner. Then we do the usual process of doing the fitment using freeze and then unfreeze. And then this is what we get at the end of the cycle, right? So we get images which are better than the low-res image, but not anywhere closer to the high-res image, right? So that's what the generator is able to produce at the first set of iterations after freeze and unfreeze. Right. So now this is time to see how the critic works, right? So what we do is we save all these generated images in a folder called ImageGen or NameGen as we call it. And then we'll send it to the critic. So the purpose of this is to make it harder for the critic to discriminate between what is this generated image and is it as good as the high-res image that we originally have, right? So that's the next part of it that we're doing. So this function we write so that we take the data set or the data loader from the generated image, and then we store it in a particular folder, right? And we will now use this particular folder to go the part of the function to do the critic. So here, this is where you create the critic data. Here we say that we include it from this folder. We include the classes. The classes are nothing but the images here, right? And then you do the transformation and we create a data mine. So this is normal data block API stuff. And then we assign it to a variable called crit data. In the case of a critic learner, and this is where I explain that we are not using a ResNet34 as a backend. Basically, we're using an already written critic learner called GAN critic. And what this is something I have at least not tried. If anybody have been able to go and dig on it, please be happy to explain it. But I didn't go and try to understand what this GAN critic is. I just took it for granted that there is a critic model that is available, which we're using in the case of Fast.ai. So this is what we do. We train it. And then at the end of this, we now put it into an iterative mode, right? So this is what Generative explains. So basically, there needs to be a switcher where it says, let the generator run for some time, generate images, then it stops, then it comes to the critic. The critic takes that and starts running and try to differentiate. Now the critic is slightly better at differentiating between, not slightly better, it is easy to differentiate in the first place because the generated images are not so great. So now we add this loss function of can the generator produce images that are good enough to fool the discriminator. So that becomes the next part of the generator cycle. So using this, now the generator becomes better at producing images that are capable of fooling the critic. It again goes to the critic runs for some time. The critic gets better at differentiating, but obviously find it's harder to differentiate now. And this cycle goes on and forth. So that is what is here in this part of the code. If you see here, right? So you basically have a critic. You basically have a generator here in learn.get. And then you have the switcher. The switcher basically is able to then decide how much of the generator needs to learn and how much of the discriminator needs to run at what timings and at what time should be the cutoff. And then we use both of this to create this GAN learner, right? So it says GAN learner from learners. It has the generator learn.get, learn_get. It has the critic, which is learn_crit, and functions like okay, so the weights _gen, this is an interesting thing that probably we need to understand. So I have kind of written that notes here, right? So basically what this is if I have a loss function of the generator, which is the pixel mean squared loss, and I have a loss function of the critic, which is the adaptive loss of the binary cross entropy loss. My loss function that I need to now take for the generator when I go through the iteration cycle is 100% of the mean squared loss and 50% of the, or 50 times of the adaptive loss of the binary cross entropy loss. So that's the ratio in which I will take, and that loss function I will apply for my generator to produce better quality images. So that's what this particular weights into gen basically means.
So Vijay, a question for you, and this is a bit of a tough one, because he just basically what he said is he said multiply by 50 and so on. Do you have any insight as to why we're doing that? Because it's not very obvious to me. So why did we pick 50? Why do we think 50 times is the right thing? Have you had a chance to look at that?
No, I haven't had a chance, but my intuition tells me basically we're giving a higher weightage to the loss of the critic so that the generator is able to produce a better quality image. That's what my intuition is, but I don't know the logic as to why it is 1 in 50.
Knowing Jeremy, he probably has done experiments and found that those are good weights.
Possibly. But I guess that it's just not clear as to why. But then, at the very start, I think he mentions that this is completely all part 2. So maybe then we will get to have much deeper insight as to why there is a huge kind of imbalance between 1 and 50.
So what you're saying is it's 50 times for your critic learner and 1 times what, sorry?
The mean squared loss of the generator.
Okay, fine. So and that was what we were using as the loss function initially.
Yes. So the loss function of the generator is the pixel mean squared loss, or just the mean squared loss between the input and the output. And the critic is the adaptive loss of the binary cross entropy loss.
Great, thank you.
Okay. So then, as we see, with this whole cycle, this just becomes better, right? So while still some details are missing, the eyes may not be as good as the target image. There may be still some pixelations and so forth, but it is much better than just what the generator produced, right? So that's what the output that we get from all of this. Right. So the question is this good enough? While it is good, it's still not accurate enough, right? So what should we do, or what could be done to make this better than what is currently there in front of us? And Jeremy's intuition leads him to believe that there should be a better loss function that helps the generator then produce better quality images. So the adaptive loss of the binary cross entropy loss probably is not the metric by which you want to do this loss function optimization for the generator. So research led to something called feature losses, right? So what is feature loss? It is explained in this particular paper. The link of the paper is there. When you get this presentation, you can get that as well. It is there in the notes by Hiromi and also in the original notebook of Fast.ai version 3. So what exactly is this perceptual loss, right? So this is how it is explained. So you have an encoder and a decoder, which is nothing but a generator and a discriminator. So if you see this image below, so you have this kind of thing here, which explains the black box. So you have an encoder, which is a generator, and then you have a discriminator. Now, in the case of a discriminator, what happens is you take the output of this, generator, you take the original high-res image or the original target image that you have, and then you pass it through a pre-trained network. In the case of this paper, they have used VGG16. And instead of then following through the complete network, including the head, what they do is take a cutoff somewhere in between and say, can I compare the output of this model at an intermediate layer, and then say, this is what the activation of high-res images, this is what the activation of generated images, and the loss function has to be that these two activations, the distance or the gap between these two activations has to be minimal. So that's what this feature loss actually is, right? In the case of this paper, the authors call them perceptual loss, but in the case of Jeremy, he wants to call this feature loss, right? So that's what this entire thing is. Very simply, if you look at it very simply, that's what it is, right? So, and this is the approach that is being formulated then as a part of this reading this paper. So you take the image generated by the generator, you fed it through a pre-trained network. Somewhere in the middle of the pre-trained layer or the pre-trained network, you compare the mean squared error and then basically try to get them better as we go along. Okay, so this is basically the workings of the paper. Of the notebook. So again, the standard thing of importing all the modules. Here, instead of Crapify, he uses the function called resize. So basically, this resize is resizing to a smaller image size and then saving it as a quality of 60. Instead of 10 and 70, it's a quality of 60. So that's what the difference between the CRAPFA function and this function. In the CRAPFA function, you also wrote something between 10 and 70, and the quality became equivalent to the number that you wrote. Whereas in this case, you just resize it and then you to a standard number, which I believe is 96 or 256, depending on what it is, and then you save it at a quality of 60. That's what this whole thing is. Again, you use the parallel function. Sorry, any question?
So just a quick one. Is there some sort of indices that where you talk about JPEG images or images being between 10 and 70, or is this something he's just made up for this exercise? Does anyone know?
At least I don't.
Okay, no, it's fine. Great, thank you.
Right, so let's just go forward. So we use the parallel to then be able to apply this to the image sets, image item list, and then we create this particular function. Okay, and then you define a function. Basically, this function, what it does is you need to create a data bunch, which is equivalent to the bit size that you mentioned here in the case of BS, and equivalent to the image size that you mentioned in the case of size. So that's what this function all about is. And then you go ahead and generate the data bunch, right, using that particular function, right? So the next set of screenshots that I have are basically trying to explain what is this gram matrix all about, right? So we have something called a gram matrix in this corresponding next set of slides that we're coming. What that is, as far as I understood, is it takes something of size 2, 3, 128, 128. It converts that to 2, 3, 1, 6, 3, 8, 4. So this 1, 6, 3, 8, 4 is nothing but 128 into 128. It converts to this. And then it again shuffles the order of this particular matrix into 2, 1, 6, 3, 8, 4/3. It multiplies that with the previous version of it. Then you get a size which is 2, 3/3. And then you divide it by 3 into 1, 6, 3, 8, 4. That's what this gram matrix is all about. Why this is done, I have no clue. But that's what this whole thing is coming out to. So that's the explanation that you see here. So you basically take the first item of this data set. You see its shape. It is 3, 128, 128. If you stack it, then you get the size 2, 3, 128, 128. If you go to the next set, he explained the function of this gram matrix. I have just tried to see what it basically does. And the output of that, of course, is 2, 3/3. So you take this size, you then do this change so that you get this 2, 3, 1, 6, 3, 8, 4. Then you do the transpose where you intersperse the sizes, and then you multiply that with the previous one, and you end up getting a 2, 3/3. And then you divide it by this 3 into 128 into 128, and you get this final number, right? So that's the whole thing of what this gram matrix is all about. Right. So now, any questions?
Yeah, I do have a question. So in the previous slide, you were using the ImageNet as your. So could you go to the previous slide, please?
This one?
No, the one before that. Yeah, you're normalizing with the ImageNet. Yeah, so I couldn't understand why we would do that, because when you're using the ImageNet stats, you're trying to classify whichever you're trying to help with classification, right? But why are you doing this here? It wasn't obviously.
Okay, so if you've followed along, in the case of the GANs, he has always used the generator first, right? And the generator has a unit, but this unit has a resonate architecture, right? For the downsampling path and the upsampling path. Instead of the original unit, which has this 4 blocks of 3 into 3 convolution, followed by 3 into 3 convolution, followed by a batch norm, which is what the original unit was. In the case of this unit learner that Jeremy has created, the backend is ResNet. So you have a downsampling path which is ResNet, and you have an upsampling path which is ResNet. That's what I understand. And it uses consistently for the generation of the image from a low res to a predicted high res image.
So what you're saying is he consistently uses the ImageNet stats?
Yes, if you're using the RESTnet as a backend, you need to normalize the image to ImageNet stats.
Right. Okay.
So that's consistent in this complete image restoration / generative adversarial network, notebooks.
Okay. Thank you.
Sorry, I think there are a lot of things in the chat. I have just not had the time to go through them. So if there's something interesting, please stop me at somewhere to, pick up and go through that.
General question around what are the useful applications of GAN. So maybe we could discuss that too.
Sure. Okay. Right. Here's the interesting bit. So this is where the feature loss is kind of mentioned, right? So when you saw the feature loss, or when he explained it in this previous slide, it was very simple, right? You take the output of the generator, you take the original high-res image, you pass it through this pre-trained network, and you don't use the complete network. You only use it until the convolution network or the convolution part ends. You compare the activation at somewhere in the middle, and then you compare the loss between the two, right? But if you see the actual feature loss that Jeremy has mentioned, it's kind of more broader, or kind of more, I should say, more inclusive than that. So you have a base loss, which is an L1 loss. L1 loss, he says you could use a mean squared loss or a loss. He just uses L1 loss because he likes it, right? So that's basically the first bit. The second bit where he explains is this pre-trained network, and this is what he explains is how you can use the convolutional part of it only, instead of going the complete part where it'll give you the 1,000 classes of ImageNet as an output. You take until the convolutional part of it using this called dot features, and then you put it in eval mode. Basically, you're saying that I only want to do inference. I don't want it to be trained, right? So I just want something to use what is already there and give me an output. You also don't want any gradients to be generated because you only want inference to be done. So that's why he says it's false. And then he goes on to find two things. So one is, what are the blocks just before there is a max pooling layer, the numbers, right? So what are these blocks that are just before this max pooling layers in this VGG16 network, which does not have the head, right? And he finds these blocks as 5, 12, 22, 32, and 42. And basically what they are nothing but ReLUs. So these ReLUs just happen before max pools, and therefore all these blocks that he's identified happen to be a ReLU layer. So he identifies them, right? And this is where he goes on to explain what it is, right? So basically this MFIT is nothing but the model, which is in this case VGG16, which is just the convolutional part of it. He then says, I want the outputs to be stored from this model, and that is available in this function called hook output. So this is something, if they followed out in the 6th lesson, he explains as to how you do heat maps, and this function hook outputs is very much used to store these outputs in the intermediate layers. So that's what we use here, right? And then there is something called layer weights, which he comes up with, which is not explained as to what these numbers are and where it is coming in from. There are some numbers that he comes up with. I really don't know what they are, but he's there. Okay, so what do we do first? We take them and run through this, model. So that's what the self.mfeet of x. This is very much like nn.linear of x or a model of x. The output of that comes. The model here is VGG16 with just the convolutional layers, right? And then you try to get the outputs of them stored in self.hooks.stored. This is where it gets interesting. So you have this original input, you have the target, right? So you just take them without even passing them through the network. First get the base loss, which is the L1 loss here. Then you pass them into the network, right? Layer by layer, and you get the feature loss multiplied by the weights, the L1 loss multiplied by the weights. So that's the second bit that he adds to the loss. The third part is he again takes them through these layers, and then he does the gram matrix transformation on top of them, multiplies the loss that he so obtains with weight squared and a number called 5 unit minus 3. Again, this must be a result of experiments. Why this is there is something that we don't know, right? So this is what it is. So this 3 things put together now becomes the feature loss, right? So it's just not the difference of activations. It's much more complex than that. So that's what is the feature loss that the critic is going to use and which the generator is going to use to better itself to produce better quality images. So the next of the stuff that we have here is pretty standard. You define a learner. So again, here, this is the part of it, which is generator. The arc again is a ResNet 34. You get the learning rates. You do a fit, right? Using the fit method, you save the results. That's what the fit function is. It runs the training cycle. It saves the weights, and it also shows the results as a part of this particular generation process. And then you do it, first you freeze, then you unfreeze, then you increase the size, again you freeze, again you unfreeze. You do it through a number of cycles. And this is what we get to see as a part of each of them, right? So in the first bit, when we took the size, which was, I think, 128, and you ran the loop with freeze, this is what the output was. Then when you do the unfreeze, this is what the output was. Then when you increase the size and you do a freeze and you run the training, this is what it is. And finally, when you run it the same 256 size with unfreeze, this is what the training and the output is. So that's the bit that comes out in each of these sections. Okay, now this is the output that we saw when we use a low resolution image, which is basically a quality of 60, right? What happens if we use a high resolution or a medium resolution image? What is the what I should say, the result that we get? So there is already a medium resolution data set that is available. It is, Jeremy has given it in the particular sections itself. We create the data bunch using that. So path_mr is basically where the medium resolution images are stored. So you run the standard stuff that you ran before. You again predict the number of classes to be 3. You load now what was the output of this bit, the thing that gave this training loop 4. So you load it with the weights of that. You assign it to the learner. The learner is already there, which is the generator, right? And then here he's trying to explain how you can take one image from the validation data set of this medium resolution size or medium resolution quality. When you take this data path, basically, and then you do this open image, what you get is something called an image class. Image class is very peculiar now to Fast.ai. What it does is it gives you 3 things. You have image.data, 4 things: image.data, image.size, image.shape, and image.show. So image.data is the tensor. Image.size is, of course, the size, what it is, the shape of it, and show basically shows the image. So that's what basically it is. Now you take this learner and you run it for this particular image that you took from the validation items, and you get a higher resolution image. And now we will compare what the original medium resolution image was. This is what it is. And then we compare it against the higher resolution image that we obtained as a part of running through this generator, right? So that's whole stuff. So if you see here, this is what I would say. This is the GAN, but there is no critic that is there. The critic is a part of the feature loss itself, right? So if you see the original, the generated elevation network that we had defined 2 things. We had a generator defined, we had a critic defined, we had losses for each, and there was a switch. You had to run the generator sometimes, then it stops, and you run the critic sometimes, then it stops. Whereas when you come to the feature loss part of it, you run the generator, and then as a part of the feature loss, run it through the VGG16 network. So that's the difference between the 2. Is this clear?
It is, yeah.
Okay. So any questions before I move on to the recurrent neural networks? Okay. So no point.
I'm gonna figure out how to mute everyone. Just give me a sec.
Vijay, you're muted.
Am I audible now?
Yep.
Yep.
Sorry. what I was trying to say is I apologize if I'm running very fast with all of these slides and stuff. It's just that too much of things to be covered. So I'm really sorry about that. But at any point of time, please feel free to stop me to ask questions. And if I can, I will answer them.
In the chat, there was the question of the applications of these GANs. Yeah, if you could say something about the applications, that would be nice.
So, okay, so I don't have any specific insights of that. Basically, where I've seen GANs being done, even in the organizations that I work, is on image restoration, right? So basically, if you see, and this is in the news as well, right? If you see what the government of Singapore has done is it has taken all its photographs, which are old, which are black and white. It has partnered with Google and using its AI in the Google Cloud platform to convert them from the black and white images to what it should be in the format of color. So that's one thing that is being done. A lot of these applications I also see could be in the form of optical character recognition and scanning, for example, right? So you have an image that is scanned via a camera. It may not be the best scan possible. How can I produce a better quality PDF just by scanning it, for example? That is also a GAN which you could use to find out from it. That's another use case that I have seen. These are the two things that at least I have seen being industrially used as a part of my working knowledge.
The other really cool application that recently came out was called De-Oldify. And I actually had the chance to interview the creator as well. So I've shared the link to it. And as far as I know, the thing that's in production by Singapore government is somewhat a variant of the same architecture as De-Oldify.
Absolutely. Yeah, you're bang on.
Another
I've seen the Oldify. That's a pretty, let's say, interesting and neat application. That's right.
And the sort of controversial or debatable application from last year was called deepfakes. So that was another area where GANs were being used.
Perfect.
Yeah, I think it's got like a lot of business applications too, which is not very straightforward. Like for example, in retail, like there's a lot of these virtual try-ons that's happening in e-commerce retail and even physical store retails, and a lot of that is based on GANs. So you put your image, and then you take the image of the apparel, and then you want to see how will that apparel look on you. So there are some other like those things are much more powerful, because then if you can see how it will look on you, then you can decide whether you will want it or not. So there are a few papers on it if you want to check it out as industrial applications.
There's no famous apps or platforms around it as far as
So I presume it's because it doesn't work well, right? So that's why there is not a maybe two reasons. It doesn't work well, and also it takes too long for it to actually show you what it will look like. So
it's more demanding.
Yeah, so I think there's one company which does it for eyeglasses. So you can do a virtual eyeglass, and that's I've seen some and it's probably a simpler one, like almost like you can think of it as Snapchat filter. Like you can just apply a Snapchat filter on you. So it's probably less of a harder problem. Like you don't even need a deep learning model for just that to happen. As long as it can show where your face is, it can just place something on your like two image overlays. So those type of applications you will see where CV tricks can do the job instead of it requiring a deep learning GAN style. I think GANs are probably not there yet for such. It's GANs that don't provide high resolution for these type of applications yet, I think.
So more on the research side for now, definitely.
I think so. I think probably more on the research side at this point.
Okay. Any other questions, feedback?
Vijay, you've done a terrific job so far, so please keep going.
Thanks for that. Fine. So now let us get into the last bit of this particular lesson, which is the recurrent neural networks. This is something that I've not been able to complete fully, but I'll try my best to explain what I understood as a part of going through this lesson, right? So basically what Jeremy tries to do is to demystify what is a recurrent neural network for various reasons. Computer vision and the convolutions pretty much clearer to understand, at least as a part of Fast.ai, because that is where I believe the strength has been seen, not just from Fast.ai, but across the industry. So what exactly is this recurrent neural network? So basically, it is nothing but a neural network with a single hidden layer, right? So it is a normal neural network, just like any other network. And you have an input, you have an activation, and you have an output. So that's what it is. So this, if you see, this is how Jeremy explains with the notations, right? So you have this rectangle box, which signifies an input. The size of it would be the equivalent to the batch size into the input size. Then you run it through some matrix product. Basically, you run it through an embedding because you're going to use it for text, and text can be so much. Instead of spending computational time on defining a weight matrix, which is like 1 encoded for some 1 in 16,000 or 1 in 17,000 words, or it could be 50,000 words, whatever it is. You do an embedding, then a ReLU of it, then you do a batch norm of it, then you run it through an activation, and then you try to do a softmax to predict what the next word is, right? That's what basically this neural network is. And if you see, this is what he explains in this bit. Suppose, say, you had a corpus of text, and what you wanted to do was to run 3 things at a time. The objective is take 2 words, run them through this series of embedding, then weight matrix multiplications, then ReLUs, then batch norms, then adding them with the second input, and again doing them through this batch norms and ReLUs, whatever, and then try to get a softmax to do the 3rd word. So this is how it kind of looks, right? The objective again is to show it is very simple. There is nothing that is mysterious about recurrent neural network. And personally, when I went through this, it kind of helped me to understand it at a much more conceptual level than probably what, if you just run nn.rnn on a PyTorch or on a keras.rnn on a TensorFlow would kind of get you. This is the same thing now for doing 3 words as inputs and predicting the 4th word, right? So if you see the notations here, the change. So you have one thing that says I am going from input to a hidden, and there is another one which says I'm going from hidden to hidden, right? So you have a green one to signify this is from input to hidden. You have an orange or saffron, whatever this color is, to signify hidden to an output. Hidden to a hidden, and then you have a blue one to show that I'm moving from a hidden to an output, right? And this triangle is nothing but an output, and this is how this whole thing looks. So you have the input being fed here. This goes through this particular hidden layer. Before it, there is an embedding, there is a ReLU, there is a batch norm happening here. It comes out, and then it gets added with the word that is coming in word 2. This again has an embedding before it comes and meets this particular activation here. They then together go through the hidden to hidden activations. They come out, they meet the 3rd word, they get added to it, and then all of this put together, then there is an activation done to find out what this 4th word is. That is what this whole thing is. So this is what you're seeing is a single RNN if you were to see it, right? So you have input, you have a weight matrix, you have a multiplication, you have an activation, and then the series of other words join, and the final word is produced. Now, let us just make it a little bit more, more sophisticated. Instead of showing this number of times that I'm going to have another word being added, I will just say this is for n number of words, right? So I have the first word. So I'll have anything but the first word coming in up till n minus words, right? So if my objective is to say I have 6 words, but I will send 5 words and I have to predict the 6th word. So you have word 1 coming in here, and this box here, this dotted box basically represents that I will have 2, 3, 4, and 5 coming in here. Each individually, they will go through the embedding layer. They will get added with the activation coming out of the previous hidden unit. They will get together added, and there is an activation coming out, and they'll get added with the next word, with the embedding done on that word, and the same process happens until the n-1 word. And the objective here is the final thing is this nth word that needs to be generated. So this is how you kind of sophisticate, or you're trying to kind of make it simple instead of showing this multiple inputs coming in through various words. Okay, so let us make it a little bit more sophisticated, right? What if I have a series of RNNs, and instead of showing that I will have the first word coming in, I have something initialized to 0, and all the words are coming through as input, right? So instead of having the word 1, which was an input, I will have something initialized to 0s as the input. It goes through an embedding, it comes out. Basically, there is nothing to be done here. It comes out, it gets added with the embedding of the first word. It goes through the activation, it comes out. Then it meets the embedding of the second word. It gets added up. Then it again goes through this activation. And again, this process repeats, right? Until the n-1th word, right? And whatever is the output of that gets added here, where the second layer of RNN is, I have something that starts with initialized to 0. Coming into this, it gets added up here. Now I have retained what is coming out of this particular layer. So I have a lot of contextual information about the words that I'm looking at. What words mean gender, what words mean nouns, what words mean prepositions, what word means questions, what word means, emotions. So there is a lot of contextual information that is, kind of created as a part of this particular RNN, for example, that gets added up here. And that kinds of makes this RNN much more richer because of that information coming in. And I guess goes through this, and this is able to produce the output in a much more better way, right? What if I then stack it in multiple ways? So I have unlooped this particular part. So if you had this was the looped structure. Here we have unlooped this. The second one is here. We have unlooped this, and they all produce the outputs, right? So you have word 1 coming in. You see what the input is, the embedding is, you do the activations. The output of it goes to the second hidden layer in this network, but also to the first one in this corresponding second layer of RNN, so as to speak, right? And that continues, and thereby contextual information from every hidden layer is passed on to the next RNN layer as well. And through this training process, all of these states that are produced, which have this contextual information, gets passed on from one to the other, both vertically and also to say horizontally, so that this model becomes much more richer with this information. Right. So this is how an RNN is kind of explained. And let us see how Jeremy talks about it when it goes through this human numbers data set. So this human numbers data set is nothing but you have a text, which basically is saying from 1 to some 10,000 or 12,000. It just says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in words, all the way till a particular n number. That's what this human numbers data set is all about. So you take that data set, and basically what you say is, let me strip each of this word, and I will store each of this word as a string in my text. That's what it is, right? So if you see here in the train text, you've taken to the first 80 characters. So it basically goes from 1 to 13. I think this 13 is lost because the last 3 words is not a part of this 80 characters. So you're basically then able to get each and every word coming in out of it. And the same goes for valid text. You're seeing the last 80 words here, right? So it goes on to what, 9,999, 9,999, up to 10,000 basically. So that's what this whole thing is. So here you take this, but you create a text list. You go through the same process of creating a data bunch, and then you see what is there in the train set. So you have this text of it. You can see here. It's called access box. It's basically, I think, the beginning of sentence, then the first character or the first word, the second word, and so forth. And similarly, be able to see it for the validation as well. There is something called a BPTT, which is, I think, what we will get to see in a much more better way in part 2. This basically, I understand, is a sliding window that goes over the data set and picks up those columns in that window, so that it takes us a batch when it processes through the RNNs. what it exactly does, I think it'll be much more clear when we see it. So then if we kind of step a little more into it, we take one batch of this validation data loader, right? We get the X and Y's out of it, and we see what this X and Y's are, right? So basically, we try to add the first 3 X's of the the batches that is coming out of this validation data loader. They all total to some 13,440. Basically, it means that I have 4,480 items into 3. So where do I get this 4,480? It is if I see each one is basically of 64 rows into 70 columns, and therefore I have this many number of words or characters, right? So when I have this in 1x1, the same in x2 and same in x3, when I total it, I get this 13,440. So basically that's the intuition to understand what this is. And if I see what are here, right? And when I do this x1 and get until the first column of that, I get these integers. Now, this shouldn't be confusing because as we know in matrix multiplication, we cannot multiply with strings. We have to multiply with numbers. So every batch has this in the form of numbers. Now, how do I get to see what these corresponding integers or strings are? Sorry, corresponding strings are for these numbers. I do that by getting something called a vocab. So vocab is nothing but it helps me to map a string to an integer and vice versa for the corpus of words that I have in my original data set. So if I use that and I have a function called textify, which is there as a part of Fast.ai, I get to see what these original strings are or the original words are. So in the case of x1, when I had these number 2, 8, 10, 11, 12, 20, I think number of them put together will give me this 8,001, 8,002, and so forth. So that's what this particular whole set is trying to help us to understand. And one thing that you need to find out or need to understand is if you see this x1, it starts with xx boss and ends at certain number or words. Whereas with the corresponding target for it, it starts with the next word, which is 8,001, right? So that's again something which is intuition because you are trying to get the next word predicted. So that's why the x's has the previous word and the y's have the next starting with the previous word. Starting with the next word. And that is consistent across all of the examples that you would see here. Right. Now, again, this is again very, very interesting, right? So let us see how you do it in a simple, model on a PyTorch framework. So you define a model using nn.module, and then you do the inits. So in the inits, what you do is, given a word, I get the embedding, and they have an embedding size for it already defined. I have a linear function between a hidden and hidden layer. I have a linear function between hidden and output, and I do a batch norm anywhere I want, right? So I define all of these functions here, and this is the forward method. So I take the first word, which is x of 0. I do go from input to hidden, which is basically embedding. Then I do a ReLU on top of it. Then I do a batch norm on top of it. And I get that particular output. Now I wait and see how many words do I have. For example, am I sending 2 words and then predicting the third word? Am I sending 4 words and predicting the 5th word? So I'm going to check the shape of this. If it is greater than 1, then I add the embedding of the next word. This is, if you see, I to H is input to hidden. I add the embedding of the next word with my output of the first word. And then I do the hidden to hidden, I do the ReLU, and I do the batch norm. And then again check, do I have one more word? Again, I take the third word, I find the embedding of the third word. I add it to the output that I got for the first 2 words. And then I go again, doing a hidden to hidden, going to a ReLU, going to a batch norm. And then finally, I will give a hidden to output because here I'm going to predict the output, right? So that's what this, if you look at very, very simply, this is. And again, you can take Fast.ai's framework, put a learner on top of it, have the data defined, run the model, define a loss function. The loss function is nothing but cross entropy. The matrix is accuracy, and I run it, right? So this is a single connected model. So basically what this is, if I look at this parlance, is this, right? So this is what this model defines, a simple single layer neural network, which is trying to represent what an RNN does. Okay. Now, again, let us see how this works in a loop. A loop is nothing but this. This is the loop, right? So how do I do this programmatically? So I do the same thing here. So I initialize to zeros. The first word, as we see here, we have initialized to zeros. That's what it does. Sorry. You initialize to zeros. And then for all the words that I have, I run through this loop. Instead of having the first word first and then looping for the rest of the words, I create a initialize to zero first, and then I loop through the entire list of words until the last word. That's what I do here. And then I do the traditional stuff of creating the learner, fitting a cycle, and so forth. Now, what if I have this in the form of stacked something like this? What if I have more than one? Then how do I do it as a part of the program? This is what it is, right? So here I have initialized this to 0. I have basically an output concatenation list. I call it, here we are calling it res. We're going through this, the first RNN layer. We're getting an output, and then we are putting it to this res. As it goes through the number of RNNs, the number of RNN layers that it needs to go through, the final one is stacked. The started stack is I'm stacking everything together into a single output. That's what it does, right? So it's again, if you have understood the previous part of it, to understand this is pretty easy. Now here, I have not carried forward the state. So the state is nothing but here, what I pass on here, from here to here, here to here, here to here. I have not stored the state. How can I store that state? That's what is here, right? So you create that state, you then stack it and you detach it, and then you finally stack it with the output and then run it through the final output to get the value. So that's what it is, right? It's if you understood the first part of it, following all of this becomes much simpler. And finally, how do you do it in a traditional nn.rnn method, right? So instead of having to write so much of code, you just have to define this nn.rnn and then the other things that you want to do. And this forward method does all for us because you know what this RNN can do, right? It has the state, which is the self attach. It has the input to hidden. It detaches itself, and then it finally does the hidden to output for us. So that's what the RNN is. A variation of this is GRU. Instead of doing RNN, you can do GRU as well, right? That's what basically all of this RNN is. It was very entertaining, I must say, and also frustrating at some point of time to go through all of this and understand. But it was a very worthwhile experience having done that. That completes lesson 7 and the RNNs as well. Any questions?
I think before there are any questions, Vijay, you've done an absolutely terrific job today. Thank you very much.
Thanks, John. Okay, so I will hand over the desktop. Whomsoever wants to do the mini presentation now, I will unshare myself. Yeah.
I'll just wait another minute for any questions and then I'll continue.
Sure.
All right, this is another part of the 5-minute paper discussion series that I started. So this paper is called To Tune or Not to Tune, and it's about how do you adapt representations to diverse tasks. This is specific to natural language processing. So I've been chasing this theme or topic of using transfer learning in NLP. I've shared both of the links inside of the Slack, both to the blog post and to the paper as well. So make sure you check it out in case you're interested. To give a bit of context to anyone who has forgotten about transfer learning in NLP, you have a pre-trained language model on, let's say, Wiki Text 103 or on Twitter, you fine tune the language model on your target corpus on whatever whatever target you're trying to solve. And then you sort of add a custom layer to accommodate the same pre-trained language model to perform whatever target task is. And why do we go through the pain of pre-training it on a language model and then fine-tuning it towards your target task? Because that supposedly gives a performance boost. It's faster and it allows you to reach much better accuracy. So it covers both of the aspects that are used in transfer learning. First, you have your pre-training, which I just spoke about, and then you have adaptation. So how do you adapt this pre-trained network towards your target task? There are two possible ways. The first one is feature extraction. So you have your frozen model, and the authors actually use this snowflake emoji to denote that. And you just extract those already frozen features and utilize them towards whatever target task is. This is useful in cases where you do not want to spend more computational power, or you want the process to be instantaneous, or for example, where you trust your previous features to be good enough. I think in those cases, you want to use this. And the other idea is of fine tuning. So that is denoted by this fire or savage emoji. So you unfreeze your model and you go ahead and fine tune it towards whatever target task is. These are the two approaches, and this paper gives a sort of guideline on what works better in what case, as per a scenario basis on different data sets. So these are the tasks that that are evaluated by the authors, and I suppose these are one of the standard tasks in NLP, the representative tasks of NLP, which are named entity recognition, sentiment analysis. This one we're familiar with from the lesson 4 of Fast.ai. 3-sentence pair tasks, natural language inference, paraphrase detection, and semantic textual similarity. Two little tricks that were mentioned in the paper that I want to highlight are discriminative learning rates. We as Fast.ai students are already familiar with it. So the authors degrade the learning rate by 0.4 times the learning rate of whatever the outer layer it was. Outer layer has your whatever learning rate you pass to the network. The layer just before that has 0.5 times the learning rate of that, so on and so forth. And the other one, again, which we're familiar with, at least in the image freezing. So you unfreeze your model layer by layer when you're doing transfer learning. And to talk about the results, so two models paper, the and the BERT, and these are modified as per the task needs. So the authors do a comparative study across all of these few data sets. These are again standard data sets in NLP. And the blue color represents that feature extraction was a better option in the case of Elmo. And that the accuracy proves that, again, fine-tuning was a better use case BERT base. And another thing from the paper that I want to highlight is the authors have also left a quick guideline for practitioners, which is as follow. So it covers 3 columns: what you've pre-trained upon, what conditions are you using to adapt it, and what is your target task. So I'll not go through the table. You can give it a look if you're interested. And I've shared both the blog post and the paper in the Slack. So I think this paper does not cover many of the tricks, but it's a sort of quick guideline to the practitioners, even NLP practitioners or researchers out there. When do you want to use your feature extraction or tune? So to not to tune. That's all from my mini presentation.
Thanks, Sanyam. Really good one.
So any other thoughts, questions from anyone before we close this call? Any questions with regards to what Sanyam just presented, or even any questions for Vijay on his stuff?
Yeah, I'd like to ask Sanyam. In that paper, there's something called natural language inference. What is that? In that list of tasks that they apply this to, one of the tasks is called natural language inference. It's the third one, NLI. Can you explain what that is? I haven't heard that before.
I'm not very familiar with the details, so in case anyone else has come across this. I'll answer your question in the Slack. I am not familiar with it.
Okay, thanks.
Great. Any other questions from anyone?
Just a general question for everyone. Please go ahead.
Yeah, actually, I just, Vijay, if you could just explain the batch sizing in the RNNs, because, you know, that part was a little confusing. You know, the batch size was 64, and then the BPDT was selected as 70. So, you know, that part was a little confusing to me during the lesson also. So if you could just explain that part again.
Vijay, you muted.
Yeah, so sorry. So Abhinav, it's also not clear to me as well, right? So basically what I understand from having done the course on Udacity is there is a sliding window of a certain size that you take on this corpus of the batch, so that you then are able to break it into this mini batches, right? So that's what the BPTT basically is able to help establish and take. How it actually works, we'll have to wait probably for part 2 to understand, or probably I can go through the previous lectures and you know, reply privately in Slack. I'm not able to explain it at a very intuitive level as of now.
Yeah, okay, because actually when I had taken the Udacity course on RNNs, and that part is still confusing to me.
Yeah, Jeremy said something about that in his lecture. He says that the batch sizes are deliberately made random sizes. So you specify what the size should be, but then it has some leeway to go plus or minus, and I don't know how much, but I mean, if you say you want a batch size of 64, it's not going to give you one batch with 100. It's going to have, you know, 64 and then 70 and then 57. You know, it's going to be some scatter. So I think that's maybe what was confusing, is that the batch sizes are not constant size.
Yeah, exactly. That is the confusing part.
Oh, that's I think a sort of augmentation technique that Fast.ai performs for us. So just to help your model generalize a bit better, that's why that happens.
It's not specific to Fast.ai, because I've heard this done in other contexts as well. In RNN. I mean, for example, Andrew Ain's class, he does the same thing.
Yeah, I had taken the Udacity MOOC on natural language processing, and this was one of the things that was there as well. You know, this part was confusing.
Great. Any last questions?
Next week we are going to start with part 2 from what I've gathered, and there is this schedule for the next meetup where I think Sanyam will do the lesson next week, right? And I inscripted myself, let's say, for a mini presentation, and I just wanted to ask you, it's called Interpretable Deep Learning in Drug Discovery, sort of a paper presentation. So I would do that next week.
Philip, why don't you also post that on the Slack channel?
On the Slack channel, yes, I will do that.
Okay, excellent. Well, thanks again to Vijay and Sanyam and Joseph for stepping in for the initial bit. All right. Well, hope to catch most of you next week. Enjoy your evening or night or whatever part of the day it is for you. All right. Thanks.
Yep. Thanks, everybody.
Congratulations.
Thanks.
Congratulations to everyone for making it through the course number 1, and looking forward to starting course number 2 next week.
Absolutely.
Absolutely.
Thanks, everyone, and thank you, Vijay.
Thanks, Arun. Bye.
Thank you. Bye-bye.